Hello, welcome to today's session about methods for effective online testing in Python. My name is Luka and I'm a data scientist at Zemanta, an Outbrain company. We are one of the bidders who participate in real-time auctions for ad space that can be found on the web. And to explain this in the easiest manner possible, let's just go through an easy example. So every time a user visits a website that is monetized with advertisements, if they are, of course, advertisements that are bought in a programmatic way through the RTB, they usually hold a widget that is the domain of SSPs, or also known as supply-side platforms. And what they do is they notify DSPs or bidders. DSPs are demand-side platforms, which we are one of them. What we do is we get a lot of data from the SSP, something like some device information, whether this is a mobile device, desktop device, and so on. We can also get things like user IDs, whether they are provided or even exist in the cookies. What we do then is we process the data that we received, we pick the best advertisement we have, and we return it with our bidding price to the SSP or ad exchange where the auctions are held. The advertiser who wins gets his ad displayed on the website, and then the user can see it and interact with it if they so please. This whole process takes about as much time as the page usually takes to load. So we have a hard constraint of less than about 100 milliseconds usually, and that also includes the latency. That means the request coming to us and also our response going back to the SSPs. And this process is so seamless for the users usually that most people don't even know it exists. If we jump into one of the problems that we will be facing or today, or rather I will try to explain it, is image cropping optimization. So we get a lot of images from our customers that's in the range of millions in our system currently, and they usually don't fit every space on the web perfectly because widgets are different sizes, they have different aspect ratios and so on. So we might get a landscape picture and we have to put it into a portrait placement. So the best solution for that we found out is usually cropping. So we just trim some part of the image away and display it as best as we can. So in this example on the site, you can see this was a portrait picture, or rather a landscape picture of a surfer. And we have to put it into a square placement. It doesn't really fit, so we have to either trim away some of the image on the left or the right side, or maybe fill it with blur like we did in the example below. So as you can see, the image does get altered, and maybe that even does affect how someone will interact with it, whether they like it and so on. In some cases, it can also tell a completely different story. So I would say that picking the best option here is quite subjective, and that's not really the best thing that we can do for our business, right? And also another problem is that we have millions of these images, like I already said, and if we want to then even combine that with something like aspect ratios, this is a humongous task that we simply can't do by hand. It's impossible. So what we want to do is we want to use statistics to determine the best crop in some way. So I would suggest here testing as you fly, as they say at NASA. So essentially you try to test something as close to production as possible, because in our case, we have a lot of outside factors that impact our performance. We submit our bid into the auctions. So that means that we are also have to take into account our competition, so other bidders, how the market itself is working currently, and so on. So the best that we can do is actually have online tests. And there are different varieties of online tests. We will go through them, but you do have to know that online tests for us give us the truly actionable results, or actually data that is factual. So we don't really have too many assumptions after we finish online testing. So for the instance of cropping, maybe the crop I prefer, you wouldn't, or the majority of people wouldn't. So actually, I would say that it works the best, but actually we would see a decline in our business metrics, which isn't something that we want. And of course, when it comes to online testing, in our case, it's great. It's very cheap to do, but that's because we do a lot of due diligence upfront, have frameworks set up, and so on. So let's talk about a bit about online tests a bit. So they are data hungry usually, which means that you will need to have a lot of examples. So usually sites like really small boutique online stores have trouble running them, but in our case, we get about, or even over 1.5 million requests per second. And that's a lot. That's magnitudes more than, let's say, Google gets. Search queries. And for us, that means that the tests can be cheaper because also, I mean, cheaper compared to developing elaborate simulation environments because they take time, a lot of engineering effort, and also usually you are making a lot of assumptions while doing different kinds of simulation environments. We also like online tests because they give us a data-driven decision and development approach, which we like. That means that we're leveraging science to actually improve our product in a manner that we actually know what's going on. So we test two new algorithms side by side, see which one performs better and by how much, and then we can go to production with the best possible option. Also, because of the whole data-driven aspect, online tests are getting a lot more traction lately in the industry, especially I'm sure you all have heard that big companies like Amazon, Netflix, Google, Facebook, and so on are running hundreds, thousands, maybe millions of tests for user engagement per day because they know that following scientific steps, they will get the best performance that they can. So one of the most common ways that is prevalent in the industry is A/B tests. They are very simple, but you still have to, let's say, go through the process to do correct A/B testing. Otherwise, you will get false results and maybe will go with the wrong decision at the end, which of course isn't something that we want. You always start off with a hypothesis, something like algorithm A and algorithm B perform the same. Then you pick a KPI as a statistical value that you will compare between the two groups. You calculate the needed examples to actually be able to use a statistical test in the end based on the distributions that you're assuming. Those tests usually have a value called statistical power. You have to reach it to actually know whether one group is better than the other. Then all you have to do is split the traffic between groups uniformly. Again, that's something that you will have to put some thought in. Maybe you want to split the actual users. So let's say user A always gets option A and user B always gets option B. That's just something to keep the user experience consistent. In our specific case with the cropping, we don't really show the same advertisements to the same user too often. So this isn't something that would decrease the user experience. So what we do is we just randomize the incoming requests. And once you reach the needed examples, all you need to do is analyze the results with some kind of a statistical test that best fits the distributions that you are assuming. The question here is then whether you can A/B test or whether we could do it. The most common issue that we run into is that if you're comparing very similar distributions, the pool of examples needed is very large, which you might say that's not a problem because, like you mentioned, we have more than 1.5 million of opportunities for bidding per second. But the thing is that we also have millions of images, and also the contexts in which the images are displayed vary vastly. So that means that if you go really granular into combinations, you actually don't see the same combination that often. And the other issue is also hard deadlines. For instance, Black Friday, there are a lot of campaigns that want to spend their budgets by Black Friday because that's what they're aiming for. And we might not have the ability to test it as much as we want or run tests as long as we want. And if you're really time constrained with tests, the exploration is usually really costly because you get only the average overall business results, which in a time constrained environment might not be something that is feasible. So what we can do to, let's say, mitigate these issues is reframe the problem of picking the best group as a multi-arm bandit problem. So multi-arm bandit problems are essentially all problems where you have a limited set of resources that you have to allocate between competing options to maximize some kind of a gain. Let's say you are trying to improve revenue generated per user. In our case, we were focusing on user engagement, so clicks was the metric we chose. And in the case of multi-arm bandit problems, it's the classic explore-exploit trade-off. And there are different strategies that you can use to solve this problem. Today, we will focus on two. One is Epsilon Greedy and the other one being Thompson Sampling. So the Epsilon Greedy approach is actually a frequentist strategy. It's very simple in the idea, let's say. You just separate the traffic into two groups. One is exploration, the other one is exploitation. Also, epsilon comes from the fact that you take a number or a percentage epsilon, that's exploration, and everything else goes into exploitation. So the exploration traffic usually gets, or rather than usually, it should get uniformly distributed across all bandits. Bandits here are the competing options that you have. And you measure the performance of said bandits on this exploration traffic. And then what you do is just apply the best bandit on the exploitation traffic. This actually allows us to reap the rewards sooner, but we know that we have some downsides here, like permanent exploration of options that we maybe want to, let's say, stop exploring sooner, and we will go over that in the demo a bit later. Most of the issues that we are facing with Epsilon Greedy are actually getting handled by Thompson Sampling pretty elegantly. Again, we will see all of that in the demonstration later, but just a bit of a more introduction to Thompson sampling. It is a Bayesian approach. You set priors for each bandit that you have, and then you sample them, compare them, you pick the best bandit that you have, and apply it. And over time, you keep updating the priors, and that's about it. So essentially, Thompson sampling works exactly as you would want multi-arm bandit problems to be solved. So you usually start with a uniform split and then start converging to the best groups more and more. So more traffic goes to the best performing bandits, and you omit all of the bandits that are performing badly or just worse than the best bandits. Of course, like I said, you can start off with uniform priors, but if you have, let's say, any prior knowledge about the problem or the groups that you are using, you can also tweak it so you have custom priors that will give you faster convergence into the best groups while still exploring everything else. But even though I said quite a few positive things about multi-arm bandits, they might not be the solution that you want, simply because, especially for Thompson sampling, you have to do a lot of trusting into the code. There are ways of testing it, like running like a AA test. That means that you're running two bandits that are perfectly the same, see what happens there. You can also run something that doesn't perform at all, compare it to something that does pretty well, and then you see if the convergence goes as you planned. Luckily, this is something that is quite easily simulated, like you will see in the demo. The other thing is it's hard to report KPI lifts. So in our case, especially, business owners like to have, let's say, reported numbers, some kind of lifts that we attained and so on. In their basic forms, multi-arm bandits don't really allow for that. And you can also run into the problem of the changing of user experience between different sessions. So if you're testing different UIs for your online store, a user might have different variants depending on when they log into the site. That might lead to confusion, which decreases the user experience overall. So that's something that can cause user drops. That's not something you want, but there are usually workarounds to all of these problems. Also, before we go further, I would like to stress some hard constraints again. Like I said, we have only 100 milliseconds per request, which includes latency. So we try to mitigate the latency issue by having a sharded net of bidders spread worldwide, which means that they have their own memory storage and so on. But to actually keep track of everything that's happening, we have to also have a central data store. And if you want to query something or even write to the central store, that's usually a really expensive operation, especially if you're looking at the 100 millisecond constraint. And also for Thompson sampling specifically, the sampling and comparing of bandits is actually a really expensive operation that can't really be done on the fly in a manner that is fast enough for our use case. So what we can do, however, is we can adjust the strategies a bit and make them actually available for online usage like we do today. We decided on using batching. So what we do is we periodically get the data and update the priors in a, let's say, on a job node that runs separately from the bidders. We sample these distributions on it, compare them, calculate weights for each bandit. And all we have to do then is pull the weights into bidders, and that's it. We do this periodically every, let's say, 5 to 10 minutes. And at bidding time, so when we are constrained with time, we only have to run a weighted lottery while bidding. And just one random and looping through an array of, let's say, up to 10 elements is actually very cheap and doesn't really have any effects on on our timeouts, how much we can bid and so on. Now let's go into the simulations a bit, so you can actually see the differences between the methods that we are using. The first one is The first thing that I would like to mention here, this is a very simple simulation environment, and the results that you will see are solely based on the plugged in numbers. They don't really represent exactly what we are seeing on our end. They might also not represent your state, but the code is available on GitHub. The link is also in the, I think, the description of this talk, so you can open it, change the factors a bit, and see how it would perform if you did something similar. If you look at the resource allocation for A/B tests, you can see that it's quite uniform. That's something not only expected but needed. If you're running online A/B tests or split tests, you want to see this in some kind of metric that you're looking at. If you're not seeing it, you might have a bug and you should really check out the code. Another thing to note here is also that all of these charts are cumulative. So that means that if we're looking at the batch 50, that means how much resources were allocated to each bandit up until the 50th batch summed up. If we now compare the last chart to the Epsilon Greedy allocation, we can already see a huge difference, but also some issues as well. So in this simulation, I added a bandit that doesn't perform at all. So it actually has the CTR of 0, which means that it doesn't generate any clicks. It performs really badly. And you can see that it persists being explored for the longevity of the test. That is something that we want to avoid. And also the first batches, as you can see, other bandits that aren't as well as good as the best one get exploited quite a bit. Another thing here is that the basic strategy is extended with the first batch being uniformly distributed, so we don't just guess or randomly pick the best bandit and exploit it, but we explore them uniformly in the first batch and then use that data to be better able to pick it in the next batch, which one should get the most data. Most of the problems that we were facing with Epsilon Greedy get handled quite nicely by Thompson sampling. As you can see that the first two bandits, so the blue and the orange one, disappear from the plot very fast because we do explore them, see that they don't work, and then we, let's say, just constrain the amount of traffic that they get to 0 at some point. But also you might notice that other than that, the chart looks quite similar to Epsilon Greedy. So at the end of the test, about as much was allocated to the best bandit as in the Epsilon Greedy case, which is also reflected in this chart where we compare the clicks received from the optimization to the actual clicks that we got at the end. So you can see that the A/B tests get a lot less clicks, but the two multi-arm bandit approaches get about the same number. So how we did the optimization is in the end is very simple. The optimization itself was implemented with Thompson sampling, which let's say covered most of the problems that we have and wanted to go through. And then we also wrapped the whole system with an A/B test to actually be able to compare, let's say, business metrics between no optimization versus using the optimization. Also, that kind of gave us the best of both worlds, right? We get the benefits of fast exploitation and also knowing how well the whole system works. So if I can impart to you a few takeaways, the first one being that online tests are great. If you can do them but aren't doing them right now, consider them. They are a great way of developing your product. If done correctly, they carry very small risks. You can wrap them in all kinds of monitoring frameworks and so on. And also